Good evening, Lamai. Right, today we are going to discuss about organic compound breaking reactions. Right, so that is actually your note number 6 in your compound synthesis institute. Right, let's discuss what these reactions are, how they look like. Right, you can clearly see, right, here these are some examples of such conversions involving the organic compound breaking reactions. Right, see what is the major difference we see with the other stuff we have learned so far, right? Okay, here we clearly see we have an organic compound as the starting compound, and that is not a straight carbon chain, right? You clearly see there is a polar bond. There is a polar bond appearing, right, at the reactant side of your organic compound, right? In your organic compound, at the reactant side, right, at the starting compound, you are seeing some polar bonds appearing here, right? So such kind of compounds are to be there, right, with these kind of synthesis processes, right? So in these cases, we have to go through the organic compound breaking reactions, right? See, if you have to analyze this thing a bit more, you clearly see this is a organic compound. As a starting material, we have organic compound. Even though it looks like we are with 5 carbons here, but still the carbon chain breaks from here. From here, some carbon oxygen bond is appearing. So this is not a straight carbon chain. This is not all about carbon-carbon linkages. Some carbon pole linkages also there. So anyway, we could clearly see this total compound is consists of a 3 carbon block and a 2 carbon block, right? So such a situation at the starting compound, and you are supposed to come up with a 5 carbon compound, right? So one may clearly think that this 3 carbon block and 2 carbon block, if you have to connect these two blocks as a carbon-carbon using a carbon-carbon bond making technique, you can come up with this final compound, right? So that is the situation of these synthesis processes, right? We are involving this organic compound breaking reactions, right? So in this case as well, you clearly see you have a compound with 5 carbons, but not all the linkages are carbon-carbon linkages. Here you clearly see some polar bond appearing, so that if you have to divide that molecule from that polar bond, you clearly see it's a 3 carbon and 2 carbon, right, compound, right? So and ultimately we are trying to come up with another kind of a compound which is also with 5 carbons, right? So anyway, there is also kind of a linkage, polar linkage is there between the N and C. You could see a polar link there, right? So anyway, so today we are going to before today's lesson, last day we had discussed about how to make these things, how to make the polar bonds, we have discussed, and before that we had discussed how to make the carbon-carbon bonds, right? Earlier we had discussed how to make the carbon-carbon bonds, carbon-carbon bond makings, right? That was discussed with the note number, right, 4, and carbon polar bond making, or the polar bond making. Polar bond making actually here, that case was discussed with our note number 5. Today we are going to discuss how to break these things. Earlier we had discussed how to form the bonds, how to form the carbon-carbon bonds and how to form the carbon polar bonds. Last day and last sessions we have discussed about those things. Today we are going to discuss about how to break the bond, how to break these polar bonds and come up with 2 different compounds. Earlier we had discussed about how 2 compounds are to bond together to make these kind of bonds, right? Today we are going to discuss about how to break these bonds, and come up with two compounds. If you are able to come up with two compounds with 3 carbon and 2 carbon, definitely we can form this one, right? If you have to come up with 3 carbon and 2 carbon blocks here as well, if you break this compound in 2 carbon and 3 carbon compounds, yes, we can ultimately come up with this thing by joining those things, right? So here our today's discussion is all about breaking these kind of larger molecules into two parts. Normally the breaking is done through the polar bond, right? So that is what we are going to discuss with our note number 6, right? Carbon compound breaking reactions, right? Organic compound breaking reactions, right? Let's start the discussion with the ester breaking. Let's start our discussion with the ester breaking, which is also known as ester hydrolysis. Let's begin with this. Ester hydrolysis. Right, ester hydrolysis. Right, let's take it as one. The first topic is about ester hydrolysis, right? Ester hydrolysis. See what this hydrolysis means? Hydrolysis means, basically lysis means the breaking. Lysis means the breaking. Hydrolysis means breaking using water. Hydro means normally hydro thing is carrying with the water. That term is involving with water. So lysis means breaking. So breaking with the use of water. That is what we are supposed to do. So we are supposed to break those esters with the use of water. Right? That is the ultimate task here with the ester hydrolysis reactions. Let's discuss about this example. So which is appearing in your tute. Right? This is an ester. All of you know this is an ester, right? This is an ester. So I'm going to break this ester into two compounds, right? So basically that breaking is done through this bond, through the ester bond, the ester hydrolysis, right? With the use of water molecules. So basically in your water molecule, right, we have a positive pole and negative pole, right? Positive poles are among the hydrogen, 2 hydrogens, and the negative pole is with the oxygen. So the water molecule will break here like this and giving the positive hydrogen to here and negative oxygen to here, right? So that is how we are supposed to break the ester bond. So OH group of the water coming towards the positive terminal of this ester bond, and the positive hydrogen of the water is coming towards the negative terminal of the ester bond, right? With this we can break the ester, right? So if you are trying to break the ester like this as a hydrolysis reaction, so first you will get the carboxylic acid, CH2CH2COOH, the carboxylic acid. You will get the carboxylic acid, and then the alcohol. You have the OH group and an R group, alcohol, right? So if you are supposed to break the ester bond, right, with the use of water, the hydrolysis reaction, right? So you would get a carboxylic acid and the alcohol theoretically, right? But we have a problem. Practically, we have a problem. What is the problem? The problem is, Lamai, to get the carboxylic acid and alcohol like this by breaking the ester, right? It will consume enormous amount of time. It will consume very large amount of time. We can't do this thing in 30 to 40 minutes. It will take much more longer time, right? So that we need to increase the reaction rate. So for that, we can use catalysts. So scientists will use catalysts to increase the hydrolysis reaction of ester, right? So as catalyst for this reaction, for this hydrolysis of esters, we can use the acids as well as bases. Acids as well as bases will act as catalysts for hydrolysis reaction of ester, right? So if you are using the acid for your hydrolysis reaction here, it is referred to as the acid hydrolysis reaction. If you are using the base as the catalyst for this reaction, it will refer as the base catalyzed hydrolysis reaction, right? We'll discuss one by one. First, we'll come up with the acid catalyzed hydrolysis reaction, which is known as the acid hydrolysis, right? I'll draw it here, acid hydrolysis thing, right? If you are to add some dill HCl, if you add some dill HCl as your catalyst, this hydrolysis reaction is referred to as acid hydrolysis. Acid hydrolysis, right? Let's see what will be products. So with the acid hydrolysis, right, you will get the carboxylic acid and alcohol in no time. With a very quick reaction, you will get the carboxylic acid and the alcohol, right? So the two products are going to be the carboxylic acid and the alcohol, respective carboxylic acid and the alcohol. This is the carboxylic acid, CH2CH2 COOH, and the alcohol. It's going to be like this, no? Alcohol. So you will get the carboxylic acid and the alcohol as your products. If you also undergo the acid catalyzed ester hydrolysis, right? Okay, but if you had used kind of a base, if you had used kind of a base to catalyze this process, the hydrolysis process of your ester, let's see what will happen. If you have to use some base as the catalyst of your hydrolysis process in your HAQ, water is very needed. Water is the reagent. No? Basically, the other guys are the acids and the stuff are the catalysts, no? Right? So reagent is always needed, right? So this is referred to as the base hydrolysis. Right? If you do a base hydrolysis, let's see what will happen. So basically, after the formation of carboxylic acid and alcohol, after the reaction, that means after the formation of carboxylic acid and alcohol, the catalyst, the NaOH, will also remain in your reaction mixture. That is what catalysts do, no? Catalysts basically involved in the reaction, but no net consumption with the catalyst, no? The starting number of moles will be there at the ultimate situation as well, right? That is what it says, that catalyst won't consume during the reaction, right? The total amount of the catalyst remains constant, right? So even after the reaction ends to form the carboxylic acid and alcohol, still your catalyst, the NaOH, the base, is remaining in your flask, right? Then what will happen? As one of these things, as one of the products you form by the hydrolysis is kind of an acid, that acid will react with the base, which is your catalyst, right? Your catalyst is the NaOH, which is a base. That thing, as it is a base, it will react with the so produce acid of the reaction, right? So as this one is a kind of acid, that guy will react with the base to form the salt. Acid-base reactions will form the salt and H2. So as a result of the base catalyzed hydrolysis of the ester, you won't get carboxylic acid, but it's salt. It's salt, right? So it will be the CH3, CH2, CO, O minus Na plus. It will be the salt, right? Because after the reaction, the catalyst is remaining in the flask, so that as it's a base, it will react with the so produce acid in your reaction, right? So the acid-base reaction, the carboxylic acid in your, the acid-base reaction will give you the salt and H2. H2O, salt and H2O. So we will get the salt as a product. And as alcohols are not having a considerable amount of acidity to react with the NaOH, it won't react. Alcohols are not with considerable acidity to react with the NaOH base, right? So it won't react, right? So the final two compounds in a base hydrolysis reaction is then going to be a carboxylated anion, the salt, and the alcohol. So these are the two products you would observe by a base catalysis of an ester. What are the two products? The carboxylated anion or the salt. Carboxylate anion or the salt, and the alcohol. So in synthesis processes, in compound synthesis processes, we can convert this carboxylate anion, we can convert that carboxylate anion into the carboxylic acid by just adding some acid. Just adding some acid, right? You can replace this Na plus with this H plus and convert this one into the carboxylic acid that will be needed in compound synthesis processes. So produced salt can be converted to the carboxylic acid by acidifying the medium, right? This is the carboxylic acid, right? So this is all about the theory part behind the acid hydrolysis reactions of esters, right? Okay, clear now? Let's use this stuff, use these theories we have learned in some conversion procedures, right? Let's come up with an example here. Let's copy this example for Ester hydrolysis reactions, right? You are starting up with this one, some ester, and you are supposed to produce this thing. This is the conversion we had started our discussion with, right? Let's see how to carry out this kind of a reaction, this kind of synthesis process, right? With the use of acid catalyst reactions, acid catalyst or base catalyst ester hydrolysis reactions, right? See, first examine the two compounds. Here, right here, at the start, you have a 5-carbon compound, but right, it is not totally a carbon-carbon linkages are there. You could clearly see some polar bond appearing at the starting compound, right? So there you could clearly see, if you were to break this bond from here, if you were to break the stuff from here, you could clearly see some 3-carbon compound and some 2-carbon compound will form. If you break the bond from the ester bond, right, you will get some 3-carbon compound and a 2-carbon compound, right? If you have to think of this side as well, you clearly see, right, some 5-carbon ultimate compound is to be formed. 5-carbon ultimate compound is to be formed, right? Let's see how to carry out this kind of a conversion, right? So first of all, if we can break this thing into two of 3-carbon and 2-carbon compounds, then we can think of joining them, the 3-carbon and 2-carbon compounds, we can think of joining them to come up with the 5-carbon compound. That is our major, right, thinking pattern here, right? So let's do the stuff like that. So I'll carry out kind of Ester hydrolysis. So let's carry out the acid hydrolysis in this case. I'm just carrying out the acid hydrolysis, right? I'm just carrying out the acid hydrolysis, right? Let's do the acid hydrolysis. Right? For the acid hydrolysis, what we need is some dill acid, dill H plus. So one can say dill H plus H2SO4 can be used, or dill HCl even. Right? I'll come with dill HCl or aqueous HCl. So what will happen? Right? If you add some dill HCl, right, two compounds will form. Right? Two compounds will form. As the bond is going to be break from this situation, from the ester bond, you will get two compounds. What are two compounds? The OH thing comes to here, the hydrogen comes to here. So you will get the carboxylic acid and the alcohol if you have to follow this kind of acid hydrolysis process, right? So you will get the CH3, CH2, right? COOH, the carboxylic acid, and the alcohol. So these two guys are not going to further react, right, with the acid there, because carboxylic acid is kind of acid, so acid is not going to react with acids, and alcohols are not showing any kind of basicity to react with the HCl, right? So the two compounds are these, the two products are these by a acid hydrolysis of an ester, right? So now we are happy. Now we are with some 3 carbon compound and a 2 carbon compound, right? So now we can think of combining these two stuff to come up with the 5 carbon compound, right? So that is our task now, right? So after this thing, just think of forming this one. This is kind of a carbon-carbon bond making, right? Here we are thinking of a carbon-carbon bond making, carbon-carbon bond making. As we are with a 3 carbon compound and 2 carbon compound, as we are with 3 carbon blocks and 2 carbon blocks, right? First we need to divide this long compound, large compound, into 3 carbon and 2 carbon blocks. That is how we are supposed to think here, right? As now we are with 3 carbon and 2 carbon blocks. In my bag, I have 2 carbon and 3 carbon blocks, right? So that I am thinking of breaking this whole compound into 2 carbon and 3 carbon blocks, right? So that thing can be done if you break from this bond. If you break from this bond, then you will come up with 3 carbon and 2 carbon blocks. 3 carbon and 2 carbon blocks, right? So as we had 3 carbon and 2 carbon blocks, I had divided this thing into, right, 3 carbon and 2 carbon blocks. That is the idea, right? So I'll use one of the techniques available here. One of the techniques. So basically, to form the carbon-carbon bonds, right? The 3 techniques are there: Grignard technique, Ester technique, and the condensation technique, right? I'll use some Grignard technique. I'll come up with the Grignard technique to make this bond. You can use the Ester technique as well as the condensation, right? Kind of a heterocondensation could be done. Right, so anyway, I'll copy the Grignard technique to join the 2 carbons, right? Okay, if you're thinking of the Grignard technique, right, these are the 2 carbons, right, which will ultimately connect, right? So I'll take this carbon is actually coming from the Grignard, and I'll take this one is actually coming from the carbonyl. So if it is so, it is only with one R group, as this block contains only one R group, it should be the aldehyde. Right, let's come up with the 2 compounds, right? The Grignard, first write the Grignard here. So write in the Grignard, that is normal. So we just write the Grignard like this. So this is the Grignard carbon. So I'll write it here, no? So it is easy to break from these guys, no? So this is the 3 carbon compound, no? This is 2 carbon compound. I'll write the 3 carbon compound and this age, so we can convert easily, right? So this is going to be the Grignard. Sorry. So this is your Grignard carbon, and that guy is with 2 R groups. right? As we are lacking of 4 bonds here, you need to come up with a hydrogen, right? You need to come up with a hydrogen, right? That is your green art, right? Then what about this aldehyde? See, this is the carbonyl carbon. This is the carbonyl carbon, right? That carbon contain one CH3 group, the R group, and as we are lacking of 4 bonds, only 3 is available. There should be a hydrogen here. There should be a hydrogen here. That is your aldehyde, right? If you connect these two guys, right? As these two carbons will connect, right? Leave in the MGBR section, right? So you would get, right? I'll write it here. This compound, CH3 is there, and the CH3, I'll bait this CH3 and write, and H is there, and to this green carbon, this aldehyde carbon will connect. This will become a OH ultimately when you are adding H plus H2O. When you are adding H plus H2O, this oxygen will become OH, right? That is the green connection, right? So you have to mix with the water, right? First the mixing, then adding some H plus H2O, right? So then it is easy to convert this into here. What you need to do is just do some hydrolysis, right? Just do some hydrolysis. Sorry, just do some dehydration. So that this OH will release this H to form the double bond there. So to do a dehydration, what you just need is the concentrated H2SO4. And you need to heat the stuff as well. That stuff is completed, right? So what about this? Connecting this one to here? Connecting this one to here is very easy. Just adding PCC will convert the primary alcohol to the aldehyde, and connecting this to here. So at the start you are with the functionality at the corner carbon, but you need the functionality to the center. So first we have to bring the function to the center. So that could be done first by water method or the HBR method, bringing the function to the center, right? So let's do that thing. So you can first come up with the alcohol. By adding lithium aluminium hydride in dry ether medium and some H plus H2O. Then you can think of coming up with the right correct positioning here. You can now think of taking the function to the center, right? So Markovnikov methods can be used there. First get rid of the water molecule, right? Then add some HBr. So to get rid of water molecule, you can come up with the conc H2SO4 and heat. So add some HBr, you can come up with the HBr. So this can be easily done by adding some magnesium in dry ether medium, form the ground region, right? So this is going to be your conversion, right? So our major learning today is all about this, how to break this large compound, this step, into two of smaller compounds, right? How to break this larger organic compound into two of smaller compounds. That was the major learning today, right? The other stuff are some we have learned through the last few days, right now. So this is kind of a conversion, and here the Ester Hydrolysis reaction. It's actually I had carried out some acid hydrolysis reaction in this case, right? Okay, so that is the ester hydrolysis we have learned, right? Okay, you can copy the stuff, right? Then we can move to the next section. Right now, okay, then we'll come up with the next topic, the second kind of hydrolysis reaction or second kind of organic compound breaking reaction. We'll study that thing. It is known as the amide hydrolysis. We'll do that. See, let's come up with an amide. Right, so I'll come up with the same compound in your right note, right? So this is kind of amide, right? So I'm supposed to break this compound into two small organic compounds, right? So we can carry out that breaking with the amide bond. So I'm supposed to break this amide bond to come up with a 3 carbon and 2 carbon, 2 compounds, right? So if you have to break this bond, with the use of water as a hydrolysis reaction, right? So what will be the two products you would observe? So the water's OH group comes to the section, while the water's H group comes to here, right? Water's positive pole comes to the negative pole of the polar bond, and the negative pole of the water, the oxygen, comes towards the positive pole of the amide bond, right? So here we are discussing about the amide hydrolysis, right? Okay, so with the amide hydrolysis, right, we would think theoretically the carboxylic acid and the amine CH3CH2 NH2, the amine, those are the primary products theoretically from a amide hydrolysis. The primary products are the carboxylic and the amine. But again, we have the same problem, right? We had with the ester hydrolysis processes. This is so time consuming. So we need to do this one quickly. For that, we use acids and bases, acid or a base as a catalyst. So if acid is used as a catalyst for this reaction, we refer that reaction as a acid catalyzed amide hydrolysis or acid hydrolysis. So if we are to use some base as our catalyst to do this process, right, we referred it as the base catalyzed amide hydrolysis or base hydrolysis reaction. Let's discuss one by one, right? First, we'll start with the acid catalyzed amide hydrolysis, right? So if you are to use kind of acid, let's as an example, let's use the dill HCl, the HClAQ. So then the process is referred to as acid hydrolysis or acid catalyzed hydrolysis. Acid hydrolysis of amides, right? See what would be the products here. So first, this carboxy acid will be made. So as carboxy acids, that won't going to react further with the acids. So after you forming the carboxy acids and the amines, the catalyst is still there at the system, at your solution. So catalyst made, as it's an acid, as the catalyst is kind of an acid, it may try to react if a base is there in your final reaction mixture. But as carboxy acid is kind of acid, that won't get reacted with the catalyst acid, right? So the carboxylic acid with the same form will appear at the ultimate flask. So one product is going to be the carboxylic acid. The next product. So what about this? So amines. So as we know, the amines are basic. As we know, the amines are basic. With the use of their lone pairs on nitrogen, they can donate these lone pairs. So that Lewis bases, amines are considered as Lewis bases. Those are basic. So these basic amines will react with the HCl. So after reaction also the HCl is there as it is the catalyst. So after the formation of amine, the HCl is there as it's a catalyst after the hydrolysis reaction. But then what will happen? Then as amines are basic, those will react with the acid in your flask, that is acid catalyst, right? So the acid base reaction will produce you the salt, the ammonium salt. See, that is going to be like this. So you have the, it's like this in Lama. So if the ammonia is to react to HCl, it will form the NH4 plus and Cl minus. What happens is you have the H plus and the Cl minus here. No? With the lone pair, this H plus will be grabbed. That is why it is said as NH4 plus and the Cl minus. That is the ammonium salt, which is going to make when the HCl is reacting with ammonia. Like that, if your HCl is going to react with this amine, what will you product? CH3, CH2, you have the NH2 here, and that will grab one of the hydrogens here. It will grab the hydrogen here. So CH3, CH2, NH2 is there. When the H plus is connected, it is going to be NH3 plus, NH2, and H plus is NH3 plus, like here, NH3 plus, and the Cl minus, right? That is going to be your salt then, right? So I'm writing that thing. That is actually, right? It will be NH3 plus the Cl minus. NH2 is there, H plus is coming from this, NH3 plus the Cl minus. And for that, this section is connected. CH2, CH3. Right, that is the salt. Right? So this is your carboxylic acid. This is your salt, right? Ammonium salt, right? So you get the ammonium salt, right? And then we can actually convert the salt into amine. We can convert the salt into amine. By just adding a base to that. Just add some base. So ammonium salt will convert to your acid. That H plus grab by the RNH2. The H plus gained by the RNH2 will be gained by the NaOH. The NaOH, as it's a base, it will attack the H plus of this thing and take that thing, leaving the RNH2 like this. So we will produce the amine ultimately like that. Right? So that is what happens with the acid catalyzed hydrolysis if you have to do the process with kind of a amide, right? So let's discuss what will happen if you use some hydrolysis reaction with the bases as a catalyst, right? Let's come up with the NaOHAQ as a catalyst. Now we are using a base. Let's see what will happen. Then the process is referred to as the base catalyzed hydrolysis or the base hydrolysis. Let's see what will products. So the product carboxy acid, which will form by the hydrolysis, right, is acidic. The carboxy acid which is formed by the hydrolysis is acidic. Then what will happen? That acidic thing will react with the catalyst. The acidic thing will react with your base here. Even after reaction, the base, the catalyst is appearing, the NaOH is appearing after producing the carboxy acid. So that NaOH will react with the carboxy acid as its base. So the base acid base reaction. So you will come up with the salt here. You won't get the carboxy acid with the base hydrolysis reactions. You get the salt there, the carboxylate salt, the carboxylate salt, right? And with this, as amines are basic, the basic guys won't react with bases. So amine guy will stand as it is. So amines will stand, right? So the two products are the carboxylate anion and the amines by a base catalyst. The salt here, the carboxylate and the salt, and the amine. So in our conversions, we can convert this stuff into familiar carboxylic acid by just adding an acid here. It's adding an acid to the salt. You can convert that into the carboxylic acid. Right? So this is the theory, right, regarding the amide hydrolysis reactions. Right, the two kinds are available: acid hydrolysis reactions and base hydrolysis reactions. That is all about the theory, right? Okay. Now let's try to discuss about a example conversion with use of the theory we learned so far, right? With use of actually the amide hydrolysis reactions. Let's do a conversion, right? So I'm going to try this example, right? So this is the example, right? So you have this starting compound with you, right? And you are supposed to, let's say you are supposed to form this one. Right? Okay. Let's examine this conversion. Right? So if you examine this one, you clearly see, right, some 5 carbon compound appearing here. 5 carbon compound appearing here as starting compound. Right? But right, if you break from here, you could come up with some 3 carbon and 2 carbon compounds, right? That is the analysis of the starting compound here. What about this one? So clearly here also you see some 5 carbon compound appearing here, but again with a carbon polar bond. Actually these two are not going to be the same, right? You clearly see this is a straight kind of a chain, but here you have some, right, branches as well. So 2 different compounds, right? Okay. So here as well, if you have to think of breaking from here, right? So you would come up with some 3 carbon and 2 carbon compounds, right? So we have to form this bond. We have to form this bond. That can be done with the use of a carbon polar bond making technique, right? So it is all about, right, polar bond makings, right? So what we have learned today is about this. This is like, you know, kind of a amide bond breaking. It's kind of a amide bond breaking. So if we can break this bond, if we can break this bond, if we can break this bond from here, you will get two compounds, one with 3 carbons and one with 2 carbons. If you break the amide bond from here, you will get two compounds, one is with 3 carbons and one is with 2 carbons. Actually, you can use those 3 carbon and 2 carbon blocks to come up with this final compound. You can connect the 3 carbon and 2 carbon blocks again to come up with this keton, right? That is the idea here, right? So first, let's start with the breaking of this amide bond, right? Okay, so I'll do some base hydrolysis here. I'll do some base hydrolysis here, right? Last time we had done an acidic hydrolysis, no? So in this case, I'm going to use some base hydrolysis. I'm going to use some NaOH to break this ester bond, sorry, amide bond, right? So by this ester hydrolysis, sorry, by this amide hydrolysis, you will get two compounds, one 3 carbon compound and one 2 carbon compound. The hydrolysis is normally done like this. The hydrogen comes to this side and the OH comes to this side, right? What are the two compounds now we are supposed to obtain? So this is kind of a carboxylic acid, this kind of carboxylic acid, but this one is kind of a base. The acid-base reaction will occur, acid-base reaction will occur to give you the salt, right? So the initial compound by the base hydrolysis of amide is going to be a salt. This is the salt, the sodium salt. And from here, as amines are basic, those guys won't react with the base further, right? So no base-base reactions. So amines will stand as they are, right? So then H2, right? So actually to do the process, continue the process, we may need to convert this into the carboxylic acid, some Amide compound. Actually that can be done with the use of a TLH plus aryl acid, right? H2SO4 HCl can be used to do this process, right? Now we are with two compounds. One is with 2 carbons, the other one is with 3 carbons. Now our task is to combine these two guys. To come up with this compound. Right? Okay. Actually, when we see this kind of polar bond makings, right? First, we can come up with the two immediate compounds responsible for making of that polar bond. We can think of the immediate two compounds responsible for making this bond, right? This is a kind of a amide bond. This kind of amide bond, right? This is a kind of amide bond. So when you think of a amide bond situation, the smaller molecule is HCl, so you have to add some H here and Cl here for the bond breaking upon forming situation, right? So if you have to react this, amine with this acid chloride, you definitely will get this amide. Right? This is the thin, right? Okay. So basically, this acid chlorides can be made by the carboxylics. Acid chlorides are normally made by the carboxylics, right, by adding some PCl3 or PCl5 to the carboxylics. So you can convert this 2 carbon compound to here, and now you can convert this 3 carbon compound to here, right? We'll do the two processes, right? Okay, first we'll convert this 2 carbon stuff to here, right? So you can convert this, that guy is kind of a oxygen compound. So before coming up with the oxygen compound, you have to convert the compound into alcohol. The alcohols will lead to the oxygen compounds, right? Use the bridge between the oxygen compound. So you can convert this thing into alcohol by just adding NaNO2HCl. That alcohol can be easily converted to carboxylic acid by H plus came in the form of this oxidizing. What about this? Converting this guy to here. Now you clearly see, right, with this one, the functional appears with the corner carbon, but here it is with the center carbon. This is center carbon. So first of all, function should be carried out to here. Function should be carried out to here, right? So let's do the stuff with the use of H2O or HBr methods. So I'll copy the H2O method, right? So, right, I'll bring that thing here. So we can convert this stuff to the alcohol by just adding lithium aluminum hydride in dry ether medium and some H plus H2O. Then we can convert this alcohol to an alkene, as we are supposed to, right, bring the functional to the center. I'll convert this into an alkene, right? Okay, that can be done with use of consider H2SO4. Then, so I'll write this here, right? Then I'll bring the functional to the center by adding some HBr. So that will bring the functional to the center, right? Now I can complete the process like that. Right, by just adding NH3, right? So this is your conversion, right? That is not that much of hard question, right? The synchronous is not that much hard, right? So basically what we have learned today is actually this thing, this procedure, right? How to, right, do the ester bond, sorry, ester and the amide bond breakings, right? Here it's kind of a amide bond breaking, right? So if we are okay with this stuff and come up with 2 compounds with 3 carbons and 2 carbons, then the task is not that hard. What you need to is actually to combine those two guys to come up with this larger compound, right? That is the whole idea, right? So this is all about the carbon polar bond breakings, right? So this is all about breaking reactions in organic compounds, right? Let's copy this stuff. right? There are three types of bond breakings are available to copy smaller compounds from larger compounds in available syllabus. Right? We had discussed about two things, the ester breaking and the amide breaking. Right? Now we are going to discuss about another one, is which is also actually a kind of ester breaking, but this in this time it is not about the hydrolysis, but it is another method, actually using lithium aluminum hydride to break the esters. Right? Let's discuss about that thing. Right? So we are moving to the third kind of bond breakings, right? So that is the ester breaking. Ester breaking with the use of lithium aluminum hydride. Right? Let's discuss about that thing. Right. Suppose you have given this kind of a ester right, this kind of ester, right? You have provided this kind of ester, and then you need to, let's say you need to copy two compounds from this one. You are supposed to copy two compounds from this one. So what you need to do there is, then you can break this ester. You can break this ester from here. You can break this ester from this ester bond, so that you can copy with some 3 carbon compound and a 2 carbon compound. Right? So this ester breaking can be done with the use of lithium aluminum hydride. See what will happen. So you can use the lithium aluminum hydride to do this process, right? So you can use the lithium aluminum hydride to do this process, right? Lithium aluminum hydride in dry ether medium to H plus H2O, right? So if you do this thing, you come up with this kind of a compound. So basically lithium aluminum hydride is known as a reagent to form alcohols. Then what will happen? So you'll come up with, this is the functional carbon, you'll come up with the alcohol from this one, right? Alcohol from this one, actually, which is carrying this R group. So alcohol is going to be made after adding the lithium hydride is actually the alcohol carrying this R group. That's the first alcohol you will form. Right? This is the functional carbon and this is the R group. So this alcohol will be produced from this side, and from this side you will get the next alcohol. Right? So this is the functional carbon. So just add some hydrogen here. This is the alcohol. Right? So by the acidic makeup, you get that alcohol, right? So those are the two compounds you will get if you add some lithium hydride to these esters, right? So it is going to be a primary alcohol and another alcohol coming from this part. Right? Right? So those are the two alcohols which are supposed to form by the lithium aluminum hydride break-in reaction. Right now? So let's use this one as well for a organic synthesis process. Let's come up with an example for this one as well. Right? Okay, let's do the stuff. Let's do some example hydrolysis reaction. Example conversion for this thing. See, say you are starting with this one. Let's copy this example. Right, and you are supposed to form this. See what we can do now. So basically, right, we can analyze this one. When you have to analyze the starting compound, if you break the ester from here, you will get some 3 carbon compound and a 2 carbon compound. 3 carbon compound and a 2 carbon compound. On the other side, as the compound to synthesize, if you break from this bond, this polar bond, you will see some 2 carbon and a 3 carbon dots appearing. Right? Okay, and this is referred to as a imine bond formation, polar bond making. So imine bond, and this is referred to as a organic compound breaking reactions. Organic compound breaking, bond breaking. Right? Okay, let's do the stuff. First, we'll break this bond and copy 2 compounds. Then, ultimately, we can connect those 3 carbon and 2 carbon dots to copy this final compound. That is our plan here. Right? So, first, let's break this one. Let's break this one. Now, we are going to use the lithium aluminum hydride to break this thing. Right? So, when using lithium aluminum hydride, you have to add the lithium aluminum hydride in the dry ether medium, and then you can do some acidic makeup. Right? So with this, what you get is actually 2 alcohols. Actually, 1 alcohol is from this section where this carbon in the functional carbon, the carbonyl carbon, the OH containing carbon, the carbonyl carbon, and you have this R group with that. So this is the first alcohol. Right, this is the functional carbon and this is the R group. Right, and with that we'll produce the alcohol from here. Right, right now. Okay, right. So now you are with a 3 carbon compound and a 2 carbon compound. Now what you need to do is just to connect those 2 guys to copy it here. Right, so first of all, we can think of the 2 compounds which are responsible for making this polar bond. Right, let's start from there by analyzing the 2 compounds which will produce this one. So this is the imine bond. For the imine bond, the smaller molecule is H2O, the 2 hydrogens comes towards the nitrogen side and the oxygen coming towards the carbon side. So if you are to react this aldehyde to this carbon, the double bond oxygen is connected. If you react this aldehyde with this amine, with this primary amine, see the primary amine, right? If you react this aldehyde with this primary amine, this double bond oxygen and this 2 hydrogens will leave, and this carbon and this nitrogen will connect. That is how we are supposed to come up with the final product, right? So now our task is simplified to converting this 3 carbon into this carbon compound, 3 carbon compound, and converting this one into this 2 carbon compound into this 2 carbon compound, right? So this is actually one step reaction. Just you have the primary alcohol and you are supposed to come up with the aldehyde. So that can be easily done, right? With the use of PCC. With the use of PCC, that can be easily done. And now we are supposed to convert this one to there, right? So at this compound, your functionality is at the corner, but at this compound, your functionality is at the center. So first of all, we need to bring this functionality to the center. We can do that thing with the use of H2O or HBr methods, right? So let's do the stuff, the note number 3 stuff, right? So first of all, you need to come up with the alkene to change the functionality towards the center carbon, right? So that can be done by dehydration. Then we need to come up with that NH2. Before that, let's bring the function to the center carbon. That can be done even by a HBr, even by the HBr technique, right? By just adding HBr. Now we can convert this Br to the NH2. Now the function is at the center. We are happy, right? Now we can convert this Br into NH2 by just adding NH3. Right? So that is our conversion. So basically, when you are using the lithium aluminum hydride dry ether, that breaking technique, normally steps are bit smaller. I mean, one step less than the ester breaking via hydrolysis reactions, right? Basically, when you are to break the ester via hydrolysis reactions, you will get the carboxylic acid and the alcohol, no? Carboxylic acid and the alcohol, no? So then the carboxylic acid we'll have to convert it. Carboxylic acid also have to convert it into the alcohol here, no? So that one more step will be consumed when you are doing the same process with the hydrolysis reactions, right? But if you are following the lithium hydride reaction, right, one less step, with the use of one less step, you can complete the process, right? That is one usage or one positive thing with the lithium aluminum hydride breaking, right? So this is kind of an example for the ester breaking with use of lithium aluminum hydride, right? So you can complete the stuff as well. Okay, so you have questions at the page number 18 in your tude, right? That question set 3 is there, right? I'll do one or two examples there, one or two questions there, right? With the use of this technique, right? So basically question number 11, 12 and 13. Question number 11, 12 and 13 are regarding this section, what we have done today, note number 6. I'll do one of those, right? So I'll come up with the question number 11 in your tude, right? This page number 18, problem set 3, the question number 11. Eleventh question, right? See what it how it appears, right? So you are supposed to start from this one, and you are supposed to come up with this compound. right now. That is the problem appearing in your question 11 at the question set 3. Right? Let's try to do this conversion. Right, with the learnings we have learned today. Right? Okay. Let's do the stuff. So first of all, you can analyze here. If you break this bond from here, if you break this bond from here, you will get a 2 carbon block and a 3 carbon block. If you have to break the total compound from here, you will get a 2 carbon compound and 3 carbon compound. Right? So we are supposed to break this compound into 2 carbon and 3 carbon blocks. We need to break this one into 2 carbon and 3 carbon blocks. So if you break this compound from here, you break this compound from here, you clearly see some 2 carbon block and a 3 carbon block will appear. Right? Okay. So you are with a 2 carbon and 3 carbon blocks here. Now, so that I have break this compound into 2 carbon and 3 carbon blocks. Right? Simple as that. Right? So the only possible breaking is from here actually to come up with 2 carbon and 3 carbon blocks. Right. Let's first break this stuff and then we can analyze from that side. So the breaking here, right, could be done by a acid hydrolysis or a base hydrolysis. Right? I'll go with the acid hydrolysis in this case. Right? So I'll come with HClAQ and some heating. And remember, Lamai, right? To hydrolyze the amides, is kind of amide, right? So to hydrolyze the amides, heating is essential. Right? Remember that. To hydrolyze an amide, heating is essential. Right? So you'll come up with what? The OH will be connected here, hydrogen will be connected to here, but as this one is a base, that will further react with HCl to come up with the salt. We'll just do that, right? So first of all, this is acid, so acid won't react with acid. So with this, you will form these 2 compounds. First the carboxylic acid, then this one as a salt, CH3, CH2, CH2, and this is going to be NH2 and this H plus, NH3 plus, and the Cl minus. So you have NH2 here and this H plus, with this H plus it is NH3 plus and the Cl minus from here, right? That is a salt. You can convert the salt into the non-amine by just adding some base. It's copied in your HAQ. So now you are clear that you are with a 2 carbon block and a 3 carbon block. Now we are supposed to bring these 2 guys together to copy this one. Right. First of all, let's examine this thing. Right. So here, this is a carbon-carbon bond forming. This is a kind of a carbon-carbon bond forming. Right. Just a carbon-carbon bond making. So you can think of Grignard method, acetylide method, as well as the condensation there. So I'll go with the acetylide method here. Last time I had used the Grignard method, no, for the carbon-carbon bond making. Now I'll come up with the acetylide method here. So if you are to use the acetylide method to make this larger compound, so acetylation should come up with a terminal carbon. So with these 2 blocks, this carbon is a terminal carbon of this block, but this is not. This carbon is actually a center carbon of this block. So acetylization should come up with the terminal carbon. So I'll take this one as the acetylide carbon. And this carbon should come up with then alkyl halide. We'll do the stuff now. So I'll write the acetylide, the 2 carbon acetylide here. So we can convert that thing from here. So 2 carbon acetylide. So 2 carbon acetylide is this. Coming from this, right? AC minus in A plus. This is acetylide, right? And then this alkyl halide. So you have this carbon, right? So you have this carbon, and that guy is with 2 R groups, the 2 CH3 groups. This is the alkyl halide carbon. That guy is with 2 CH3 groups. As this guy is lack of 4 bonds, you have to add some hydrogen, right? So some hydrogen is there, right now. Okay. Now, if you connect these 2 guys, right? If you can do these 2 guys, right? This guy will connect with this one, and Br will leave with the sodium plus, right? So what you will obtain is, right, this one. Some CH is there, some triple bond will appear, right? I'll connect it here, no? It's better. I'll connect this one from here, right? The H is here, and triple bond will be there like this, and to that this carbon will connect. This is carbon, these are 2 carbons connected, right? And with that carbon you have H and a 2 CH3s, H and a 2 CH3s, right? So with one single step you can come to here, right? You can come to here with one single step, right? So that is just hydrating this bond, that can be done with H2PDO, H2 nickel low, H2 platinum, right now. So our major task is to convert these 2 guys to these 2 cases, right? So we can convert this one to here. This is a triple bond. Before this acetylide, we should copy the triple bond, the terminal alkyne, So that can be done with use of sodium or NaNH2. So now we need to copy this, right? So before they are making the triple bond, first you need to copy the double bond there. For a double bond, adding 2 BRs for the double bond by adding 2 BRs and removing the 2 HBr molecules. That is how the triple bond is made. Right? To this thing, you just add the Br to CCl4, and to this one you just remove the 2 of HBr to complete 2 5 bonds. That is done by alcoholic KOH, right? Okay. So to convert this one to here, what we could do? So first of all, you need to copy the alcohol, that can be done by lithium aluminum hydride, N2H plus H2O, and this thing can be done by dehydration, just adding conc H2SO4 and heating, right? So like this we can convert the stuff to the acetylide, and then that acetylide should be connected with this one. So let's try to convert this one to this alkyl halide. So here you have the corner carbon as the functionality, functional carbon. So you have to bring that to here. So H2O HBr technique should be followed. So I'll do so. First of all, you can convert this one to the OH, and that OH can be converted to a double bond. Right? This is just adding NaNO2HCl, and this is just dehydrating. And this can be done by adding some HBr. Right now, so this is your conversion. Right, that is the conversion number 11, appearing at the page number 18, which is actually the problem set 3. Right now, so you can complete this stuff, right? Right, with this actually we are completing the aliphatic conversions. Actually we are done with the aliphatic conversions, right? So we'll wind up at this session with this learning, right? Then we have another sections regarding conversions, that is all about the benzene conversions. We'll study that thing in the next lesson, the conversions related to benzene, right? Okay, until then, goodbye.